These ladder problems are really classic problems in statics, and you can tell why. If you ever put a ladder up against a house or a wall to go paint the house or hang a picture, you'd really like that ladder to stay at rest. You do not want it to move. So they're really classic problems here, and they're usually set up like this. Here's a ladder here leaning up against a wall, and there's friction down here at the bottom. And you know that you never want to put a ladder down here on a very slippery surface. You want as much friction down here as possible to hold that end of the ladder. The wall here can or cannot have friction, depending on what the problem is asking for, say that you're studying, but we'll just assume that the wall is frictionless. And that may not be such a bad approximation. Typically, we don't expect this end of the ladder sliding against the wall to hold very much. And so, off we go there. Okay, so that's sort of the situation. The ladder has a length L and the mass M, so that's sort of the params of the ladder. So what we need to do first is we like to think that the ladder to stay at rest, obviously. So the sum of the x forces are going to be equal to 0. The sum of the y forces is equal to 0. And of course the sum of the torques are going to be 0 also. So those are our three guiding equations. Before we get into them, obviously forces are needed to fill in those two equations right there. And forces are also the generators of these torques here. So the first thing we should do is to go ahead and identify all the forces on the ladder. Okay? So the easy one usually is the weight of the ladder. Right here to the center, we can draw a big fat mg. That's the weight of the ladder. So yes, the weight of the ladder alone could cause it to fall. So that's going to be an important force. We also have the wall pushing on the ladder this way, something like that. We'll label it F of the wall, something like that. We also have the normal force of the ground pushing up on the ladder like that. We'll just call it N like that. And again, if the ladder is sitting like this and we don't want it to slide, we don't want this end over here to start sliding that way, then there'll be a frictional force on the ladder, and I'll just sort of draw it this way because that's going to be our frictional force of interest right there. We just don't want it to slide this way, so we're going to expect the static friction is going to oppose that motion and point to the right like that. Okay? So those are the four forces on the ladder, so why don't we just get into it then and start filling in our equations here. So the first one we have is that the sum of the x forces are equal to 0. So if you just identify all the x forces, and we'll use a sign convention that looks like this, usual thing. Up is positive, down is negative, right is positive, left is negative, something like that. Let's just start filling in. I've got the force of the wall, minus force of the wall, and I've got the frictional force down here. These are all x-directed forces. I don't see any others, so that's equal to 0. And you have one conclusion for yourself right there, in particular that the force the wall has to exert on the ladder exactly opposes friction. So as the ladder leans up against the wall, it causes the wall molecules to flex a bit in there. The wall will have a small dent in it right there, and that exactly is equal and opposite to the frictional force that must be supplied down here to keep the ladder from moving. So there's a conclusion for you right there. Nothing definitive yet, but a little bit of intuition into the problem. Now the sum of the y forces are equal to 0. In the y direction, I have the normal force up, that's this one right here, and I have the weight of the ladder down, and that'll be equal to 0. And so that I have then that the normal force of the ground is just equal to the weight of the ladder. And I hope that probably makes some intuitive sense now. So the amount of upwards push the ground has to support the whole of the ladder is exactly equal to the downwards weight of the ladder right there. It's a little bit more intuition, but no real hardcore solutions just yet. But now I can supply the sum of the torques equal to 0, and that's the more tricky one, but let's see what I get. Of course, for torques, the first thing I should do is set up a pivot point somewhere, and for this I'll go ahead and set my pivot point right here. Reason being is because there's two unknown forces down here, the normal force of the ground and the frictional force. So by setting the pivot there, the moment arm will be 0, and those two forces will not appear in my torque equation. So let's see what we get. And we'll just remember that my working equation for torque is RF times the sine of theta. Okay, so if I start at the pivot, I don't include the normal friction force because they have 0 moment arm. But as I go up the ladder now, I do encounter the weight of the ladder at the halfway point. And again, I'll apply a sign convention that looks something like this, positive or negative. And so in my torque equation now, I'm going to start filling that in. The first term will be L over 2 times mg times the sine of 90 minus theta. So you want to be a little careful with the angles in there now. L over 2 is the moment arm of the weight acting in L over 2 from the axis rotation. Mg is the force itself. And we need the sine of the angle between the moment arm, which is right here, and this downwards force. So if this is theta, this is a 90-degree angle. This angle here must be 90 minus theta. So that's where I got that angle from there. And yeah, the cosine of 90 minus theta is, the sine of 90 minus theta is the cosine, but not important at this point, okay? Keep on going up the ladder, and the last force I see that could possibly torque on the ladder here is the wall force right here. That's going to be a minus sign in front of it because if that wall force had its way, it would cause the ladder to rotate like this. That's this way, a negative direction. So it acts as a full L of the ladder, that's the moment arm, times the wall force, then they'll have the sine of theta in there. So where did I get the sine of theta in this case? Well, if this is theta right here, then this angle in here, which is the angle between the moment arm, which is a line that connects the axis of rotation and the point of application of force, and the force itself, this angle here is the same as that angle, so that'll be an angle theta in there as well. Can't see it very well, but that's exactly what happens there. And so that's sort of it for the torque equation. There are no other torques on the ladder, so all that's going to be equal to 0. And if I do a bit of simplification now, this is actually sort of worth looking at here. The L is going to cancel out right there and there. And if we write this sine of 90 minus theta as the cosine of theta, then the result actually gets pretty succinct here. We'll get something like mg times the cosine of theta is equal to the wall force times the sine of theta. That's a bit of just algebra in there. Then if I additionally sort of simplify a bit more, I'll get mg divided by the wall force here is equal to the tangent of theta, because sine over cosine is equal to tangent. So we're definitely getting somewhere now. And what you can notice is now we can maybe do a bit of combination over here with these two items right here. How? Because we know that the definition of friction force over here is still mu times the normal force. That means the wall force then is just mu times the normal force. But we can see from this equation right here that the normal force is just capital M times G. It's that downward force of the wall. So see, we actually know what the wall force is. It is the friction force, which is mu times the normal force, but the normal force is the full weight of the ladder. So there's your wall force right there. And yes, you can now substitute that in here, and what you'll get is 1 over mu is equal to the tangent of theta. So this is sort of a little result for the ladder right here, that if you want the ladder to stay static at some angle theta, so you want to orient the ladder to be at some angle theta, choose it like this, whatever you want this to be. You know, whether you want 45 degrees, 63 degrees, whatever. That's sort of where let's just call it your ladder orientation. Pick it, whatever you want. But if you want it to stay, then you better have a coefficient of friction that's related to the angle in this way. So the coefficient of friction, if you wanted to solve it this way, must be 1 over the tangent of that angle that you want the ladder to stick at. So that's sort of the relation for the way the ladder comes down. You should be prepared then in problems like this as they expand, maybe on an exam or something like that, that you could definitely increase the difficulty level of the problem and get some different results. If you put something like a painter climbing up the ladder, and say the painter here was a distance x from the pivot point, the painter would then exert another downwards weight on the ladder. I'll call it little mg, and you should be able to wrap that up into, say, the sum of your y force and your torque equation to see how the ladder, the painter going up the ladder some distance x would affect the whole thing. So a very common question would be, how far up the ladder could the painter go before the ladder slips? That might be something you should think about. So there you go, ladder problems.